Hello everyone, welcome back to Dragonfly Engineering. My name is Dave Eberhardt, and this week we're going to be bringing up a small KUKA robot that I purchased on eBay. It's still bolted onto the pallet that it came in, and I'm going to show you the setup and operation, a basic beginner operation of these small KUKA robots. Most of these I buy on eBay. Actually, I think I only purchased one new. Every single one of these robots is a different color because for some reason the folks on eBay who resell these robots wind up making them different colors. And here we've got a kinematic mount with an end effector and an end effector cube that Quinn from Blondie Hacks made for Dragonfly Engineering. And I'd like to extend a special thank you to Quinn for collaborating with Dragonfly Engineering. It was a big help to the show, and thank you very much. And for those who don't know, I actually met up with Quinn at the Good of the Land Festival 2019. And that's where a bunch of YouTube creators met up at this festival in Texas. I met with her and a few other YouTubers, and that's what sparked off this collaboration. So Quinn, thank you very much, and I look forward to working with you some more. All right, so without further ado, let's get into the basics of the KUKA robot. So I think I might get the GoPro and walk around with that. That may be a little more efficient. So 1 second. All right, so I guess we could start with the robot itself. This is a 6-axis robot, and the axes are axis 1, and they're labeled here. So this axis 1 spins this direction. Axis 2 is right here. Axis 3 is up here. Axis 4 is what's called the wrist, and it spins this direction. Axis 5 is also, I guess you could call the wrist as well, which spins this way. And axis 6 is where the Blondie Hacks end effector is bolted to, and this one rotates this direction. Up here on the wrist, I guess this is the forearm, there is pneumatic connections and electrical connections so that you don't have to string cable all the way down. There's pneumatic switches inside, but I need to confirm that. I know one of them definitely does, but I would have to see if all of them have that. And then, so back here is the connections. So this is the main power cable. This connection here, I believe, is a data cable, and then there's a ground cable, and then air connections which lead up to the end effector area. Over here is the controller box. This is a KR-C4 compact, and let's see if the screen is still working. Yeah, so on this controller, this is the other end of the power cable. This is the data cable going to the robot. Power input, power switch. This is the teach pendant cable. This cable here is called the X11 connection, which has all of your safety switches like emergency stop, safety cage door switches, and all sorts of switches. So there's like 20 circuits in here, most of which you short out unless you use them for safety cages and things like that. The X12 connection here, this is all of the IOs. So there's 16 inputs and 16 outputs, which you can use to sense things, like to switch things on and off. For the inputs and then the outputs, it outputs a 24-volt source to turn on things like air cylinders or grippers or other signals to other equipment. So I usually do pretty simple setups. So I basically just use these 16 inputs and 16 outputs to talk to other equipment and also to turn on accessories that are bolted onto the end effector of the robot. And of course over here is the ground, which is a temporary ground, because you do need to ground the robot to the control box. And all of this is powered by 220 volt single phase, which I've temporarily set up with this transformer. So this is the setup. Oh, and then the teach pendant is over here. This guy right here. And I don't think I can show the software interface. There may be copyright problems with KUKA. Okay, so I powered up the robot controller, and it's found the robot and synchronized its settings to this particular robot. I've got the emergency stop circuit installed with the X11 connector, and this is the teach pendant, which also has an emergency stop button on it. The operation of this robot is done in a few modes. Right now we're in teach mode on the robot, and that allows me to freely move the axes around, either in axis mode or world coordinate system mode. And the other mode is you flip a switch, automatic. And basically you run it in automatic, the robot, once you've taught it a program to execute. There's also a external trigger mode for larger automation systems that have PLC robot controllers all over the place. So this system can be tied into a much larger control matrix, if you will, but we won't get into that. So right now we're in teach mode. For this teach pendant, this is where you actually control the robot motion. There is something called a panic button or a panic bar on the bottom. Let me zoom in so you can see. So this white bar you have to hold down, and if you can hear when I hold this bar down halfway, you can hear all the switches in the robot controller turn on. Now, when you're operating this robot, you have to have your finger on this panic bar. And it's called a panic bar because if you push too far, like that, then the robot will stop moving because it assumes that it's about to, it's racing towards you and it's about to squish you. So a human, when they're controlling something like this, when they see that they're about to get banged up by the robot, they'll clench up and hit this panic bar. There's one here for the left-hand people, one for the right-hand people. And there's another one up here for the trigger holding people like this. I like to use the bar on the side myself. So and then you've got to, if you hit the panic bar or you press too hard on this operate button, which means emergency stop basically, then you have to acknowledge with the controller that you're no longer panicked and you can continue working. So I'm going to show how that works. So we're going to move an A. So I'm going to hold down the control button, and you hear the switches activate the robot. And then if we move, and I don't like where it's moving, I'm going to clench up, and you can see how the robot stopped moving immediately, and the circuit breakers kicked in the controller. So now I'm going to go ahead and confirm with the controller that I'm no longer panicked, and then we can go back to operation by holding down the control button in the middle position. The other thing with this control button is if you start to get lazy and your fingers get fatigued, you'll start to release the button and then the robot will also stop. So you gotta keep your fingers hovered in the middle of this panic bar. Okay, so we are in axis mode right now, which is the simplest mode for these 6-axis robots. And there's axis 1 through 6. Axis 1 is the bottom axis all the way up to axis 6. I can kind of show you. So this is axis 1. We're spinning around like so. And then axis 6 is the very top, the end effector itself. And then all of the other axes are the different wrists locations throughout the robot. So this is 3, this is axis 2, and axis 1. The other mode of operation for this robot controller is world coordinate system. And so I'm going to switch to world coordinate system now. So instead of each individual axis moving, the robot is now going to calculate all of the motions in the axes to keep this cube in the right orientation as it exists when we entered into world coordinate system. And it will, if we tell the cube to move in X, then the angles of the cube will remain fixed, but the cube will move in the x-axis or minus x. And if we tell it to move in y, then again the orientation of the cube remains the same, but it will translate in space in x and y. So let's demonstrate that. So let's do y minus. And I think the axis is not quite lined up with the camera angle, but you get the idea. So here we're going to move the cube from minus y to plus y. You can see how the robot's keeping the orientation of the cube the same. Of course, we hit a workspace here. Whoever had this robot before set up a workspace envelope, like a virtual wall, so the robot won't allow anything to go past that wall. That's why it stopped. And I acknowledged that it hit a workspace error, so we'll just not go that far. So let's go move back in Y, and now we can move. Oh, and like I mentioned earlier, this is bolted down to a wooden pallet, so the robot's going to jitter as it stops, which is a good example of why you need to bolt these robots down to a very robust foundation, because there's a lot of inertial forces involved. Let's move an X in the world coordinate system. It's going to move it towards me, and then we can move the cube away from me. Again, keeping the orientation the same until we reach the end of the reach of the robot. And then we can do the same with Z-axis. So it'll keep the cube oriented and then move it down until we hit the limit of the wrist travel. Let's move up like so. So that is essentially the world coordinate system. We can set our own coordinate systems as well by teaching with a lot of times I use a number 2 pencil. One, because if it breaks, it's not that big of a deal. But you sharpen a pencil and you use the tip of a pencil to find or define planes in space, and you can teach other coordinate systems with the robot. So these coordinate systems can, be like a 45-degree plane. They can be above the robot. You can have the robot hanging from the ceiling, and you can have a coordinate system down below it. Or you can set up multiple coordinate systems all the way around so that you don't have to fuss with dealing with interpolating positions correctly. If you just define a workspace, and then the robot will do all the math to figure out how to operate in some angled workspace. But I typically just stick with the world coordinate system because my work I do here is relatively simple. So now we can look at angles in the world coordinate system. Okay, I set up another camera angle for our tool end effector on the robot here, so we can orient the 3 angles so we can try to get an idea of where the center of the virtual tool is. I think the tool center is actually on the flange here, so let's see what happens with, we'll start with angle A, and this is in the world coordinate system. So we'll spin A, and there we go, we're just basically spinning on the axis 6 of the robot without much other action happening. Let's get back to the, okay, and then we'll try angle B. So here's B, and you can see how we're spinning around, looks to be the base of the flange. So we went to a limit switch, so we'll go B minus. Yeah, so I think we're on the default original tool definition, which is a 0 point right here, or in the center of this mounting flange. So let's move B back to our initial position, like so. And then we'll start playing with the angle C on the end effector here. So here you can see it. Let me change the camera angle. Okay, so this is angle C, and you'll be able to see how the robot is moving all of its body parts to keep the center of the mounting flange or the cylinder of the end effector in the right position. And I hit a limit switch on the axis again. So let's go the other direction, and you'll kind of see how the robot is working out all of its motions to keep everything the same except for one angle on the end effector. So there's how it's kind of moving its body around, holding the center of the tool in space, which is kind of cool, and it shows there's a lot of math involved in these robot controllers. Okay, so let's go back to the XYZ coordinate system, or move X, Y, and Z without changing the angle of the tool, so you can get an idea of how the interpolation of the axes will move the X, Y, and Z in space. So there you can see the cube isn't really changing angles or orientation, but it's translating in space. The robot's calculating how to do all of that until it reaches its full stretch limit, which is close to there. And then if we come back to the original position, again, this is all world coordinate system. Okay, so we're back with the robot, and we're about to write our first program for the robot, just to demonstrate how to teach a program in the robot and then execute the program. And if we got time, then we can also set up the gripper here with an output from the robot controller. and an air cylinder and a pneumatic valve to essentially activate this gripper here to pick something up if we've got time. So the first thing that we want to do in a program is to enter into a new program. So that's essentially a platform that has what's called a home position, and then the body of the program, and then at the end of the program is another home position. That's the simplest type of program. The programming for these robots goes, infinitely complicated. But for most of what I do, it's just I start at a home position, tell the robot to do a bunch of stuff, and then to conclude the program, the robot goes back to its home position and then is ready to repeat the process in usually an infinite loop with a trigger that says get out of the loop when it's the end of the day. So I've already set the home position to this location, which is the beginning of our program, and I've loaded a program into the controller. The next step is to start to move the robot around to different positions and teach those positions. There's two types of position. Well, there's more than two types of position, but for this discussion we're going to talk about linear motion and point-to-point motion. Point-to-point motion is a motion where the robot figures out from its current location how to get to the new location, let's say here, as efficiently as possible, which can a lot of times lead to the end effector of the robot going off axis or kind of arcing around to get to the position most effectively with the robot. Now the other mode is obviously linear motions, in which case the robot goes through more trouble to keep the cube or the end effector cube in a straight line to the new position. And usually that's a safer way to program the robot because a lot of times at the point-to-point operation, the cube will start to go off what you imagine is the appropriate axis or path to follow, and you can wind up banging into stuff just because as a human it seems the most obvious thing is to move the cube from this position to this position in a straight line. But to the robot motors it doesn't necessarily work that way. So I typically do almost all of my work programming the robots with linear motion calls. So let's go ahead and do that. So I've already actually programmed the first position. So let's, I'm going to reset the program I've started, and we can go to the first position, which is there. So this is the first linear motion. And right now the program, if I wanted to say, okay, I'm done with the program, then the robot would just go back to the home position, which is what it was in before we moved to this first position, but that's not very interesting. So what we're going to do now is I'm going to manually operate this controller with my finger on the panic button, and we are going to move down in Z. So we're going to imagine we're going to pick up some object off this pallet. So what we're going to do is, let's see, hopefully this will remain in frame, but I'm going to hold down the panic button and then tell the robot to move down in Z. And the gripper there is kind of representative of something we're going to pick up off of the floor. So there we go. That looks like a good position, and I'm going to tell it to teach this position. So I'm telling it to do instead of a point-to-point motion, I'm going to tell it a linear motion with a velocity of 1 meter per second. I'm slowing things down because I don't want the robot to tear itself out of this particle board plywood surface on this pallet. So I say okay, command okay. And now at this point I would give a command to close the pincher with an output from the X12 connector. And this output is actually a 24 volt voltage source, a DC voltage source from a digital I/O pack inside of the controller. We can open the cover up and I can show you that in a little bit here. But effectively there's 16 outputs and there's 16 options on this controller to turn on any output at any time, and also read 16 inputs, which are 24 volt inputs to the controller. So it's real handy to do things like turn on grippers and things. So, but we'll skip that for now because I don't know if we have time for me to hook up all the wiring and everything today. but I wanted to show you the simple programming of this robot. So in the future, we're going to add a step to gripper close, which would be output 1, 24 volts. Signal would be high, which would activate a pneumatic solenoid to turn on air pressure to the gripper. But let's skip that for now. So imagine it just grabbed something. So now we're going to move back up in Z to stick the thing that we just grabbed somewhere. So we can tell it to do another linear position. So we're going to teach this new position as linear, and then Command OK. And then we're going to go ahead and place the object someplace else, like maybe, I don't have a big workspace here. Maybe onto this stool right here. If you can, yeah, you can see that stool. Okay, so our next action would be to go, let's see here, I think it's Y positive. And the robot's going to come over and then probably come back a little bit in X, so we can place our object on the stool. And a lot of times with robot controlling, you want to do pounce positions. So in fact, that being said, I think we're going to go higher up in Z. Okay, so we're going to teach, actually we're going to move over to make sure we clear the stool. And I'm going to tell it to do a linear point recording, and it recorded that point. And then we can go forward in Y, make sure we cleared the stool. And we can go down in Z to there. And I'm going to do another command, linear. Oh, I remembered that I'm doing linear. That's nice of it. And that's it. And then at this point, we would give a command to turn off output 1, which would open the pincher and release and place the object on the stool. And then the default program end for this template is a point-to-point motion back to home, which is that orientation that we saw at the beginning. So I think we are done with writing the program. Again, this is a very simplified view of the program. A lot of times you spend hours fussing getting the orientation just right, because these robots are accurate to within a thousandth of an inch in this entire workspace. So a lot of times there's real delicate, finicky stuff where you're getting down sometimes with a microscope and you have the motion slowed way down, the jog slowed way down, so you're moving a few thousandths at a time to place an object exactly in the right spot that you want. But we're not doing that for this demonstration. So I'm going to go ahead and, let's see, reset this program. And then the next step in the teach mode is to actually go through the motions that we just taught it. The robot really, I don't think, will allow you to go to automatic mode unless it knows that you ran through the program that you just wrote in teach mode in the slow, controlled manner with your finger on the panic button the whole time. So what I'm going to do now is hold down the panic button, and I'm going to hit a little play icon on this controller, and it should take us back to the home position, which is here. And then it actually tells us, yes, you are home and on the programmed path that the robot is going to follow. And then it's called a BCO motion. I forgot what BCO stands for, but it basically says we're back on the ideal path that I'm programmed to do. And now I'm going to hold down the panic button again, and then I'm going to hold the play button, and this program is going to go through the sequence of events, one point at a time, and show us how it's going to play. And if I don't like anything, then I can always hit the emergency stop, or this emergency stop, or just push in on the panic button and everything will stop. But here you can see how we're going to go over and clear the, whoops. Oh, I guess I never recorded the actual final position to place the object on the stool. So now I can hit the reverse play button, and the robot will actually go back up into the different points recorded in the program to the last point, which is point 2 in this case. And then I'm going to go ahead and in the editing mode of this software, I can now jog the robot around and then actually teach this point. I don't know why I didn't teach it before. So this is going to be our position where we're going to release the clamp. So I'm going to say motion and linear, and then command OK. So now we should have a point 21, and then the point-to-point motion back to home. So let's go ahead and play this through. So I'm at that new position in the program, and now I'm telling it to continue playing the program, and the last step is to go back home, which is just like that. And then the program ended. So in the program there's a little thing that says end. So we can reset the program. Now we're still in the teach mode, so I'm gonna go ahead and hold down the panic button again, and we're going to run through this little program that we just wrote. So we're going to go down Z and grab the part. We're going to lift it up, put it on top of our stool. And these are all the coordinations that are linear. Except the final motion is just 1 point. Then we're going to release the part, and then go back home. And there you have it. So our program successfully executed. So the next step is to switch the mode of this controller to automatic. Now in automatic mode, there's no more panic button. So the only thing you can do at this point is to hit the emergency stop button, or this emergency stop button. So in automatic mode, I'm going to reset. And similar to when you start a new program on your CNC mill, when you first run a program on one of these industrial robots, you want to slow down the play speed so you can override the velocity that the robot executes your program all the way down to 1%. So we're gonna do a 10% velocity override for this first operation, or this first execution of the program, after we've already confirmed that it performed the operations that we want in teach mode. So to execute the program, there's a different button on the bottom. You hit this green button, and I usually, like just with a CNC mill, I like to have my finger ready on the emergency stop. So we're going to hit the green button, and it's going to tell us that we are at the patch, or the path has been reached for the program, or the BCO run, which means, okay, we are on path and ready to go. So the next time I pull this green trigger, the program is going to execute. And of course I've got it at 10%, so it's not going to go very fast, which is what you want to do. There's my first point. Going to the second point. I should go over this. And get ready to pull the part of the grip. And then come over to the place position. And release, and go home. So there we go. Let me increase the velocity up to 100%. So these velocities are going to be 1 meter per second. I don't want to go to the maximum, which is 2 meters per second, because I don't want to damage the mount on this wooden base. Okay, so reset program, and then I'm going to hit the green button again, and it says BCO reached. Basically, you hit the start button twice every time. And here we go. Whoop. Looks like we had a maximum velocity error on axis 4. So we were close to the singularity, and a lot of times the robot, to keep the 1 meter per second, it'll spin its wrist too fast. So what we need to do now is fix that problem. Or we can run the program slower to not exceed the velocity, but it sounded like it was spinning pretty quick. So I will go ahead and confirm that error. Now we got to go back to teach mode. And it's pretty common to run into these singularity points where the axis 6 and the axis 4 are aligned, and the robot can't figure out what to do. It'll start going into like a 1 over x mathematical situation where it'll say, okay, for me to maintain the math, the velocity on axis 4 needs to go to infinity. So it tries to do that until it hits the maximum velocity limit for that axis. So a lot of times you can fix this problem by just spinning one of the axes off and then reteaching that position. So let's spin axis 5 like that. I hope you can see that in the screen. And then we can do a touch up. So I'm going to touch up that spot. And then we can reset the program. When you do like changes to points in the middle of the program, a lot of times you have to go back to the beginning of the program or go back to the home position, which is there. And then we will go ahead and run the program again in teach mode. So to do an actual production setup on a robot like this, you're looking at a few hours of this kind of fuss, basically avoiding all of the singularity points. Like right there, you see how we spun off axis. So the math is a lot easier on the robot, and the accelerations are a lot easier. And that's also, you know, you can see in the home position, I have the wrist is rotated up off axis from the other axis, just to help stay out of the singularity points. Okay, so let's, I'll reduce the velocity of to execute the program to 50%. So we'll hit the automatic execution start, and that was the first click. It says it's locked and loaded. And then our second, and let me reduce the velocity to 50, and then we'll hit again, and we'll see if we can get past that singularity point. So we'll pick up the part, and then we'll spin off axis a little bit, and like that at 50% velocity. And then that was the, that was full velocity, or actually 50% velocity for returning home, the point-to-point home velocity. I may update that to 50%. Let's go a little bit faster. Again, I don't want to rip off the bottom of the robot from the plywood. Okay, let's do one more. This is 75% of 1 meter per second. So reset, and then so we're in automatic mode. So I'm going to go ahead and hit the start key again. So this is 75% and 50% velocity reduction at the return to home. And we probably shouldn't go much faster than that. So so that last velocity that you saw was like 40% of the max velocity. So anything faster, I really need to have this robot bolted down to a solid steel foundation. Otherwise, it's gonna fling itself across the shop here, and we don't want that. Anyway, so that is simple programming of a super basic operation. So let me see if I've got time to set up the digital IOs to get one output so we can actually turn our gripper on and off. So let's go ahead and take a look at the digital IO that I was telling you about. When I say digital IO, that means a digital input and output for signals out of the X12 connector, which is currently just a unpopulated D-sub type of connector here. So anyway, looking inside the cabinet, you know, this voltage or this power is on, so you know, observe appropriate precautions. But these are this is the guts of the instrument. A lot of dust in here. Again, this is straight off eBay, so. But yeah, we can talk about what's going on inside of here real quick. So this is the motherboard. So it's a regular PC motherboard running some form of Windows. And then the processor is underneath this heatsink here. There's also backup batteries. There's a couple of 12 volt like motorcycle lead acid batteries down here. And then over here is, I forgot what this is called, but this handles all the relays and things, the interfaces, and I think it's also the safety computer. So my understanding is that these KRC4 controllers, this is a compact version of it, has a computer that controls the robot, and then there's a second independent computer that is monitoring the safety to make sure that nothing is going off with the robot itself. It's monitoring all the emergency stop buttons. It's double checking the position of the robot and making sure that nothing wrong happened with the first computer. And if the second computer says something's not right, then it says, stop everything. So I could be wrong about that. I'm not an expert about these, but that is my understanding, that there's a monitoring computer that makes sure everything is good with the first computer. The digital I/O is, or digital input output device, is this Ethernet Beck-off device, an EtherCAT device. And you can see how all of these wires are inputs and output signals. So let me get the controller. All of these little LEDs indicate input and output triggers. So I'm going to attempt to turn on one of the outputs. Well, hold on, I gotta drop the camera and then do it. So, value on, okay. All right, I'm back, because they make it so you need both hands to turn on the output. But you can see that LED light right there, that's a very good sign. That means that this module, this Beckhoff digital input-output device, is actually outputting a signal to channel 1. So up here on the X12 connector, in fact, you can follow the wire track along to basically that connector right there. So if I trace the wire that corresponds to that LED right there, that output channel 1, over to this connector, then I've got 24 volts at probably 300 milliamps to turn on or off a pneumatic valve, which in turn would turn on compressed air, which would activate this gripper. Okay, we're back. So I was able to actually kludge together a gripper for our robot to demonstrate picking and placing of a probably R2-D2 right here. So if we look at the setup here, this is a dual or a 5-way valve. So essentially you use these valves to switch pressure from what is now grip open to grip close. And then when you flip the pressures, when you apply 24 volts to this solenoid, compressed side of the gripper is vented out through these ports. So basically you just buy this 5-way valve, I think is what it's called, and you hook it up to the dual acting gripper. So right now there's air pressure holding the gripper open. And then we've got 24 volt lines which go to channel 1 of our X12 connector. You can kind of see there, I've got that one wire coming out. And then the other end is going to ground of the controller. Yeah, and then this is the air pressure which pipes into the top of this wrist. And then the robots actually have an airline that goes all the way down to the bottom and then comes out here. And this one may actually have valve controls inside, in which case this valve is not needed, but I haven't configured or even discovered to see if there is valves inside of here. And then all of that goes to shop air. So let's go ahead and add the grip or pick and then place options to our program that we wrote. Okay, so here's our piece of work that we're going to pick up. It's a R2-D2. Okay, so we'll start moving down to R2-D2. Now normally you would teach the robot to go to the place where the work is located, but in our case I'm just going to stick R2-D2 right in the jaw. Just like so. And then logic, and then wait. And we're going to tell it to wait for 1 second. And then the next command is going to be, let's see, logic out, output 1, state will be true, which that's computer jargon for saying we're going to turn on output 1, which is connected to our air cylinder. And it's going to stay on continuously. We also have the option to have it pulse or all sorts of other schemes, but let's say we're just going to keep the grip or the output 1 on, which is gripper closed in our case. Okay, and then what we're going to do is continue to play the program. So imagine that the gripper is, oh, it actually grabbed it, okay. I guess it does outputs in teach mode. Okay, so we grabbed onto R2-D2. So now we're going to go and pick up R2-D2. And hopefully we don't smash R2-D2 into the table, which we are. So what I need to do is I need to teach the updated position for this place of the R2-D2. So we're going to do Z plus, and then we're going to go, I want to make sure you can still see this in the camera. And now what we're going to do is I'm going to do another command for wait. It's a good idea to kind of let things settle in a little bit. You know, if things are vibrating or R2-D2 is flinging around, then we don't want to release while work is trying to fly off of where it needs to wind up being. Okay, and then we're going to do a command, logic output, and then out, instead of the state being true, we're going to say that the state is false, which is a fancy computer way of saying turn off output 1. So command OK, and then when I play this forward, it should turn off. like so. And then the robot started to go to its home position because that's the next line in the code. So now what we're going to do is I am going to tell it to move up out of the location where R2-D2 is and back, like so, so that R2-D2 can stay there, and then up, so up and back. And then I'm going to teach this position as linear as well. Position and command OK. The final command is to go to home. So let's go ahead and play that. Okay, I got the GoPro down there. So after 1 second, the gripper should grab R2-D2. There it goes. And picks him up. Comes down, sets him, and then we are done. And obviously we need to refine, that's where the fiddly half hour of getting the gripper and everything just right comes into play. I think we're gonna run this guy at 50% just to see how far R2-D2 is flung. Okay, so let's go ahead and click the first trigger to say that we're at the BCO path is reached. And now we're gonna go ahead and pull the trigger to start the grip, or the pick in place of R2-D2. There we go. Hang in there, R2-D2. I'm gonna set him down. And success. So there you go, we did it. All right, well that concludes our adventures of setting up a KUKA robot purchased off eBay. Everything worked out pretty good. A lot of times these robots, when you buy them secondhand, have strange configurations in them from whoever had them before. Because again, I do a lot of simple interfacing with these robots, but these can get extremely complicated with all sorts of software packages and safety protocol packages and external automation systems. So when you get this robot and it doesn't work correctly, it's probably because there's old software and old configurations in it that need to be fixed. You can call KUKA and they can help you out. There's a software called Work Visual that KUKA has for free on their website, where you actually interface with the controller and you configure your robot to work in basic mode. And a lot of times it means deleting half-installed safety protocols or things that prevent the robot to run in automatic mode, like missing equipment, missing outside interfaces and stuff. The other thing with KUKA that you should be aware of if you decide to buy one of these, either new or used, is that there really isn't any instructions that come with these robots. The manual is mostly disclaimer warnings from lawyers and piecemeal schematics and a bunch of information that is potentially misleading, but definitely won't allow you to understand how to operate this robot like I've shown you today. KUKA really would like you to, and I think the reason why their manual is so difficult to follow is that ideally you should take the KUKA training class on how to operate these things professionally and safely. And that's what I wound up having to do. So I bought a robot like 10 years ago and I tried to use it and I had no idea what I was doing. So I wound up going to Michigan and taking a 3-day class on how to operate the robot. And in that class you get the actual user manual, or the, what do they call it? The training manual for Robot Programming 1. It cost me, with flights and everything, about $2,500, I think. So when you buy a KUKA, you should just plan on spending an extra $2 to $3 grand to go to Michigan and learn how to use it. What I'm showing you here is basically for entertainment value. The most important thing is the safety factor. I'm not really covering a lot of safety, and thus you need to be professionally trained on how to use these so that you don't wind up killing yourself in the process, because these little robots can break arms or knock you out, and of course this big robot will squish you real quick. So anyway, I hope that's helpful, and if you're wondering why your robot doesn't work, it's because you need to take the class from KUKA. Otherwise you're just going to be wasting hours and hours trying to figure out why it's not working. Anyway, so with that, I will see you guys next week. All right, bye, thanks.